So we're going to continue now with momentum. We're done with mass conservation. We did both the integral and differential form. Now we're going to go after momentum. We're going to start with the integral form and then essentially ditch that and focus on the differential form. So the next order of business is to apply in Newton's second law. We're going to apply Newton's second law of motion. Okay. So Newton's second law tells us that the rate of change of momentum of a system, so dmu by dt, so this is for a system. Now you recognize that this d is essentially the system derivative, the material derivative, whatever you want to call it. It's equal to to the summation of external forces exerted on the system. Okay. Now to apply the Reynolds transport theorem, we essentially need to convert this guy to an Eulerian form. So we need to recognize extensive and intensive properties. So in this case, B is equal to mu, and therefore our intensive property is essentially dB by dm, or just the velocity. So this means that dmu by dt, Reynolds transport theorem, is partial by partial t of the integral over the control volume of rho u dv. Always write v this way, plus integral over the control surface of rho u. This is going to be interesting. U dot n ds equals summation of forces. Okay. So all you had to do is just put in your intensive property over here. Okay. When we had mass, the intensive property was 1. So we had d dt d rho integral rho dv, and over here rho times 1 times u dot n ds. But over here you have something interesting, rho u dot n ds. Okay. So we'll talk about how we evaluate that. Now, there's a couple of limitations here in that in this integral form, this applies only to this form to an inertial control volume that is not accelerating. Okay, so if you were to apply this integral momentum form to something that's moving like a rocket motor, for example, and you have a change in the thrust and you're calculating the forces, you know, you got to do a few things differently, but we're not going to, it's doable. We're not going to worry about that because our goal is to get to the differential form. And the differential form is going to, that doesn't care about the inertial volume or not, okay? But what we're going to use this for is actually to determine the external forces. So we use the integral form to say, you know, you open up a water hose or you have a rocket motor on a test bed. What is the thrust being caused by that rocket engine? You know the velocity, and then you can deduce the external forces on it. Okay, so that's kind of how it's useful, what it's useful for in the integral form. Okay, so keep that in mind, not accelerating. And there's a simple way to fix this, essentially. So if you, let's say you have a car and you put on it a gas turbine, and you might go really fast. You want to draw a control volume around it. Well, the car is moving, so your control volume is gonna move and accelerate with it. To avoid that, just bolt the car down and run it, and then you have a fixed non-moving control, non-accelerating control volume. Now, this is a vector equation. This is a vector equation. So in other words, I will refer to those as the momentum equations because there's 3 of them, right? So in the x direction, you have, right over here, in the x direction, you will have d by dt of integral rho ux dv, okay, plus, pay attention here. Which one are we changing? This u or this u? So the x component of this equation, which velocity becomes ux? This one or this one? This one, because that's the quantity we are transporting. This u dot n is always there, regardless of the intensive property. The intensive property could be anything, could be phi. In this case, just happens to be the velocity, and we're taking the x component of that velocity. So this would be rho ux u dot n ds. What this describes, then summation of forces in the x direction. What this is telling you, this is essentially calculating the flux of the x momentum across all the surfaces. So because you can still transport x momentum in the y direction with the y velocity, right? And you can still transport the y momentum in the x direction. Okay? So that's what's tricky about momentum. It's because it's a vector. So, and that vector is transported by the velocity vector, and therefore each component is transported in all 3 directions. Okay, so same thing with the y direction, you get d by dt integral control volume, rho uy dv plus integral over the control surface, rho uy u dot n ds equals summation of forces in the y direction, and etc. Now, the summation of the external forces, you might think that they're going to be different for the system than they are for the control volume. Well, they are not. Because the way we derive the Reynolds transport theorem, we said it's at the instant when the system coincides with our arbitrary control volume. And at that instant, the forces are going to be identical, the external forces. Okay? Because they're acting externally on the system or the control volume, it doesn't matter. Right? So because the system coincides with the control volume, right? So this kind of tells you internally, or like kind of what's going on as the flux move in and out, but the summation of forces, they're gonna act these are external forces. They're acting equally on the system as the control volume because they don't know if this is a control volume or a system. We're just acting in that region, right? So those don't change. That's why you don't see this right-hand side changing from Eulerian to Lagrangian. Okay? Okay. Now, like I said, we're not going to use this form a lot like we did with mass conservation. We're just going to use it to try to deduce forces exerted on a control volume, like thrust, for example. Now, something really useful happens when you choose your control volume in a way such that the surfaces are kind of aligned with the inlets and the outlets so that u dot n becomes either u out or u in, right? So it simplifies. And then rho times u, that becomes essentially mass flow rate, right? Kilogram per meter cube times meter per second, you get kilogram per second per unit area, right? But you get a flow rate over here. Okay, and that's why this becomes, this becomes useful. We'll do a couple of examples. If you had taken fluid mechanics in undergrad, this you would have spent a lot of time doing these sorts of calculations. So I'll give you a simple example of a, here's a simple example of this rocket motor. Okay, so we're going to take a, so I did a lot of work on solid, liquid, and hybrid rocket motors in my PhD. So I like to give them as examples all the time. Okay, so you got a nozzle over here. So we're going to consider a solid rocket motor. If you've never seen a rocket motor fire, a solid rocket motor fire, you should. I actually saw the one before last two shuttle launches in Florida. It was one of the most beautiful things if you could ever see. I mean, those living by some of the Air Force bases where they launch, specifically from Florida. I mean, going to a rocket launch is one of the most amazing things you could see. If you're somewhere, SpaceX is launching, go and see a launch. It's absolutely majestic. It will blow your mind. Just the immensity of it. So in a solid rocket motor, typically what you have a solid propellant grain, which is essentially pre-mixed. So you have your fuel and oxidizer pre-mixed in solid form. Once you burn it, you cannot turn it off. That's it. You're done. So ATK, a defense company, they do testing actually in Utah as well. If you can, go to one of those tests and see them, you can Google them on YouTube. It's just beautiful stuff. Anyway, so what happens once you burn this, once this ignites, hot, very hot gases, they come in kind of perpendicularly over here. They're like all compressed, etc. And then they start flowing out. So in my PhD, I developed analytical solutions for this flow field over here. What happens inside the rocket motor? Okay. Those were inviscid and viscous. Okay. So now to avoid the issue of an accelerating rocket motor, we're going to we're going to anchor this to the ground. Okay. Going to anchor it to the ground. It doesn't move. And the objective is to find the force, the thrust force created by this engine. Okay. So what we're going to do, we're going to draw a control surface around the entire engine. Okay. All of these surfaces, the velocity is 0 over here, right? Because we picked, this is solid, right? There's no flow going in, no flow going out, except over here. We're going to assume that this is uniform in average velocity, u out, going out in this direction, okay? Now, as the hot gases come out, right, they're going to push, the engine is going to move in that direction. And so on this control volume, the thrust force, the reaction force is in this direction, okay? So just matter of reference. So that's the reaction on the control volume, okay? So now we apply the momentum equations in this integral form. We have d by dt of integral over the control volume of rho u dv plus integral over the control surface of rho u dot n ds equal summation of forces. We're going to assume there are no other forces because you can neglect the pressure from the atmosphere. You can pick you can put this surface far away where kind of the gases have already dissipated somehow. Okay, and so you have like an equal pressure distribution. So no forces from the pressure. The only force is this thrust force. Okay, you assume steady state. So this is 0. d by dt is equal to 0. Steady state. Steady state. Now for this guy, the only control surface that matters is the outlet surface, right? So over the outlet surface, okay? And you have rho u out times u out, correct? Times ds equal Fe. Now u out is constant, density, we also assume it's constant. So you get rho u out, or let's call it u out times the area equal Fe. That simply is expressed as, so rho u out times A is the mass flow rate. So F, the thrust force, is the mass flow rate times the exit velocity. Simplest thrust formula ever. You can find this on the NASA website, actually. Don't be afraid to make an assumption. So here I made crazy assumptions like, yeah, density is constant, velocity, I assume it to be constant, just looking at the average velocity. This is better than nothing. You could be stuck in this integral forever. Oh, how am I going to calculate this integral? In the end, the net thrust is going to look like this. Is it going to vary a little bit? Absolutely, but at least this gives you an idea of what the thrust is. So the integral form of the momentum equations helps you in determining really the external forces, in this case on large systems. But once we go inside the fluid, we're going to look at different external forces on the control volume. Once we go to an infinitesimal control volume, then that's where the differential form becomes extremely useful. But the integral form, you rarely know the external forces. Instead, you're using the left-hand side to determine the external forces, okay? Same concept applies to a hose, water hose, firefighter, okay? So the force exerted on them and the reaction they're exerting on the hose to hold it together is proportional to the mass flow rate coming out and the velocity. And it makes sense. So the mass flow rate is constant for water, but if they close the opening, they're going to have to, hold it tighter, right? Because you've increased U out to maintain the mass flow rate. So U out increased. M dot is constant, but you close the hose a little bit, so U out is larger. So it's going to exert a larger force on you, right? Okay. Let me see. Okay, so we have a few minutes. Let's talk about these infamous external forces, okay? So like I said, the integral momentum form, you'll do a couple of homework problems on it, and that's it. We're going to forget it, okay? It's very useful, okay? But, that's part of the undergraduate in you, okay? Let me put it this way. Okay. Now, what about these external forces? So it's cool and good, but that's not going to be helpful to come up with a differential form. Okay, we need to know what these external forces are. Okay, so let me write the momentum theorem again. D by dt of the integral of rho u dv plus this control volume plus integral over the control surface of the control volume rho u dot n ds equal summation of forces. Okay. So what can you think of, in a fluid? Okay. Very small control volume. What are the external forces on the fluid, on this very small fluid element? Exerted by the fluid on it, by all the other fluid elements on this fluid element, or this control volume. What are the external forces? What's acting on it? Gravity, okay. External forces, okay. Gravity, what else? Pressure. Those are kind of intuitive, right? Magnetism, maybe. If it's a ferrous fluid, if it's got iron in it or some metal, it might be affected by magnetic forces. Yes, I was going to say that. So friction, or more kind of colloquially, is viscous forces. But I really love that you said friction, because it's better, I think, than saying viscous. Viscous seems like condescending. Oh no, we got the viscous forces over here. Friction. Friction. Why friction, Ali? Why? Eli. Why friction?
Because if the fluid pass over a surface, there will be a tension between those,
Yeah,
and that
yes.
causes friction.
Yeah. So at any point in the flow, other points are messing up with that point. They're kind of scrubbing it. We want to destroy you or something, kind of alter your shape, right? Friction. That's viscous forces. Okay. So I agree. We're going to focus on gravity, pressure, and friction. This one, not today, but it's the same. It's of the same level as the gravitational force. Okay. There's a further distinction. I'll say that distinction and we leave, between what we call body forces and surface forces. Body forces are forces that act on the entire body of the fluid, such as gravity acts on all of you, right? Surface forces, however, act locally depending on the surface orientation and whatever's going on locally. For gravity, it doesn't matter if you're standing like this or standing like that or flying in the air, it's just going to pull you down. With viscous forces, friction or pressure is different depending on the surface where you're at. So they are surface forces. So this one is a body force, and this is a surface force, surface F, then surface F. And we can continue that discussion on Wednesday. Okay, thank you.